Wolfe Creek crater was settled science, a young impact, maybe 300,000 years old. Then, a team drilled below the surface and pulled samples dated at 2.71 billion years. That was only the start of what they got wrong. This massive scar in the Tanami Desert of remote Western Australia spans roughly 875 meters across. Wolfe Creek, known locally as Candamalal, stood as a textbook example of a simple, pristine impact structure. The classic bowl shape and intact rim suggested a relatively straightforward history. Standard geological models placed the event during the late Pleistocene epoch, estimating that a stony chondrite meteorite struck the region only 120,000 years ago. Because the dry desert air limited erosion, the crater remained well preserved, serving as a baseline for studying youthful planetary collisions. It was an established geologic landmark, a completed chapter in the study of Earth's violent past. There was no reason to suspect the ground itself held a far older, vastly different story. Anomalous magnetic susceptibility from airborne surveys and elevated nickel and cobalt levels in surface samples suggested the old model was missing something. To find answers, a research team returned to the remote basin with a heavy hydraulic drill rig, turning the desert landmark into an active field laboratory. They targeted deep, unweathered material that could preserve the crater's original chemical signature, far below the reach of wind and rain. The team sunk 3 boreholes, designated C01, C02, and C03, to depths of 120, 85, and 97 meters. Retrieving an average of 85% of the rock core, the drill barrels brought up pristine layers of glassy impact, melt, and fractured breccia. This physical evidence moved the investigation beyond surface-level speculation, providing the raw, unaltered material needed to reconstruct the violent event. Under polarized light, the recovered quartz grains displayed distinct planar deformation features, microscopic cracks known as Type I and Type II PDFS. These fractures only form under shock pressures exceeding 15 gigapascals, proving a massive cosmic collision. Deeper within the melt glass matrix, scanning electron microscopy reveals coesite and stishovite, high-pressure silica polymorphs requiring pressures upwards of 30 gigapascals. But the defining clues are chemical. Embedded within the amorphous glass are spherical iron-nickel alloy droplets. Geochemical analysis of these metallic residues reveals a pronounced iridium spike of approximately 4 parts per billion, accompanied by a nickel-to-chromium ratio greater than 3. This specific geochemical fingerprint does not match a typical stony chondrite. Instead, the high gallium and platinum group element signatures point directly to the metallic core of a differentiated asteroid, a rare, iron-rich 3AB meteorite. Inside the Western Australian Argon Isotope Facility at Curtin University, researchers analyzed 12 pristine impact glass shards recovered from the drill core. Using the precise argon 40 argon 39-step heating technique, they extracted isotopic ratios from the quenched material. The analysis yielded a highly concordant plateau age of 2.71 billion years, plus or minus 0.07 billion years. This single definitive date replaced the long-accepted late Pleistocene model, which had placed the impact at a mere 120,000 years ago. To verify this massive temporal shift, researchers performed cosmogenic beryllium 10 exposure dating on the surrounding target rocks, which returned a corroborating age of approximately 2.6 billion years. The results place the Wolfe Creek impact in the deep past. The crater is a Neo-Archean structure, preserved through billions of years of gradual burial and eventual exhumation. The collision occurred when Earth's crust was still young, establishing this desert landmark as the oldest simple impact crater preserved on the planet. The newly established age transforms a remote outback destination into an essential calibration point for planetary science. Finding an intact, simple crater preserved from Earth's earliest history challenges previous models of crustal survival and erosion. Most ancient structures were swallowed by tectonic plates or ground away by ice, but this desert basin offers a rare physical record of deep-time bombardment. Scientists now use this site to calculate how often large objects struck the young Earth, filling a massive gap in historical impact rates. A single geologic anomaly in the Tanami Desert has reshaped the broader understanding of planetary evolution. Long before drills pierced the basin, the Djaru people preserved their own record of this place, which they call Kandamalal. Their oral tradition describes a bright fireball, a star fall that struck the Earth and opened the Great Circular Hole. Today, Djaru custodians act as essential partners in the ongoing research, ensuring the site is protected. While the Neo-Archean age redefines the geology, the scientific record remains unfinished. Existing cores only reach 120 meters. Revealing the full history will require deeper drilling, refined isotopic dating, and continued, respectful collaboration on the desert floor. Earth's oldest scars are still rewriting our cosmic history. If Kandamalal was misread for decades, what other planetary secrets remain hidden? Share your thoughts below.